Hello AP Stats students. Today we're going to be working on section 5.2, talking about some rules that we have to work with and learn about when we're dealing with probability. So the topics we're going to look at here today, we're going to split this section into a couple different videos. What we're going to look at today is how we describe what a probability model is. This is going to be a way that we basically identify what's everything that can happen. And secondly, we're going to be looking at some of these basic probability rules, including what's called the complement rule and the addition rule. Some of these rules and then working with two-way tables and Venn diagrams are going to be modeled and illustrated in a second video. So let's talk about probability models first. We just finished section 5.1 where we're working with simulations to try and imitate and pretend to do these random behaviors, but we can also think about just what could happen and not have to pretend to do it. We can just try to describe what all of the outcomes are. So when we describe random behavior, there's always going to be two pieces that we want to think about. One is what's called the sample space, and the sample space is basically just listing, hey, here's everything that could happen. For example, if you are playing a game of cards and you have a full deck of cards and you say, well, what could happen if I draw a card out? The sample space would have 52 things in it because there's 52 unique cards in any deck. And what a probability model is then, a probability model takes that sample space one step further. And it says, first off, what is the sample space? What are all these things that can happen? But then it also includes what's the probability of each of those things happening. So we put not only what can happen, but what the probability is as well. And so what we're going to focus on in this video is working with probability models to try and describe some random behaviors and then calculate some probabilities from it. So here's a probability model that I think you guys are all familiar with. This is a probability model showing you what can happen if you just roll two dice. So anytime you roll two dice, there are actually 36 totally unique and different things that can happen. And you know, you're familiar with all of these. You play these in board games for like Yahtzee, Monopoly. You can get a 1 and a 1 called Snake Eyes. You can get a 6 and a 6. You can get anything in between. Do notice that some of these things, for example, here's a 2 and a 3. That is a different outcome than a 3 and a 2. And you can kind of tell that by thinking about if you use two different colors of dice, that an orange 2 and a blue 3 is a different outcome than an orange 3 and a blue 2. So we want to keep track. There are ultimately 36 totally different things that can happen. One way that you could have figured that is you could think, well, there's 6 things that happen on the first die, and there's 6 things that can happen on the second die. So 6 times 6 gives us 36 total. So our sample space has 36 different outcomes, and because we have fair dice, every single one of those 36 outcomes is equally likely. So the probability of each of these is just 1 out of 36. So the chance that you roll double 6s is just the same as the chance that you roll double 1s. It's just the same as the chance that you roll a 4 and a 3. They're all equally likely. So we're going to try and take this and use a probability model here in a second with it. But first we're going to define what an event is. An event is just a particular thing that you're interested in happening. So when we work with events and probability, we're going to give them little abbreviations. We're going to usually use capital letters to say like event A, event B, and I'll give you some examples of these. But some of the notation we're going to do, if A is some event that we're interested in, then I'm going to write the probability of A by using this symbolism. We're going to put a capital P, we're going to put event A in parentheses. And so imagine this, I'm playing a dice game and I have to get a 5. A total of 5. Like I need 5 spaces. I got to move 5 spaces to get to Boardwalk and Monopoly. And I want to know what is the probability that I get a total of 5? What's the chance that I actually end up there? So one way to picture is think about all those 36 outcomes that we just saw in the previous slide and think about which ones of them actually give me a total of 5. So you can get a 1 and a 4, but you can also get a 4 and a 1. You can get a 2 and a 3, you can get a 3 and a 2. And there's no other way you can get a total of 5. So the probability of this we can calculate, and I'm going to come over here, we're going to look at this. The probability of getting a total of 5 is 4 out of 36. Okay, there's our total. And it's 4 out of 36 because there's 4 different outcomes that lead to that out of the 36 total. But what if we wanted to ask this question? What's the probability if I define event B as the sum is not a 5. So now imagine, like, if I get a 5, I'm going to land in jail or something like that on the board game. So I want to know, oh, what's the chance I don't get a 5? Well, one way you could do it is you could go back to that board and the sample space and look and count all of the different ways that are not 5. And there's a lot of them. There's actually 32 different things that are not leading to a total of 5. And so we could, by just looking back at that, say the probability of event B not getting a 5, we could go back to that sample space and count them out and say it's 32 out of 36. But sometimes there's so much to count that it's easier to think of this in a different way. And a different way to figure it is, say, the probability of B, I could figure by taking the total probability of 1 and subtracting away the outcomes that I don't want. There's a 4 out of 36 chance that I do get a 5, so if I take those away, then I'll be left with what is the probability that I don't get the 5. Now, if you're wondering where that 1 is coming from, that 1 is basically saying there's 36 total outcomes. I'm going to take away the 4 that lead to what I'm not interested in. They lead me to going to jail. They lead me to getting a 5. So I can calculate the probability. Sometimes it's easier to say, what's the probability of what I don't want, and take that away from the number 1. Okay? Now that's a rule in probability. That's called the complement rule. And what we're doing is we're saying the probability of B is 1 take away the probability of B. And I'm going to put another symbol up here. I'm going to get different colors so you see it. Okay, that B with a subscript, or sorry, like looking like an exponent C, that's called a complement. B complement means everything except for event B. So if event B meant you didn't get a 5, B complement means you did get a 5. And so that's actually what I'm writing right here. This is the way that I solved the problem in this manner up here. Either way, we get to the same answer, but sometimes one method is easier. All right, let's keep going with this here. So now we're going to look back at coin flipping. So I want you to picture that we're flipping a coin again, except this time you're going to flip a coin 3 times in a row. And you're just simply going to keep track of, did you get heads, did you get tails on each one of those 3 coin flips. And so we're going to try and answer 3 things. We're going to wonder, first off, what's the sample space? What are all the things that can happen? We're going to try and create a probability model from that. So we're going to list not only what can happen, but what are the probabilities of them. And then finally, we're going to say an event A is defined as this. Event A is you got at least 1 tail. And can we find the probability of that happening? So we're going to jump back over here to the Jamboard and do this problem. So now, in order for me to think about what is the sample space, I've got to think about what are all of the outcomes that could happen. So I'll give you an example. You could flip 3 coins and get heads, heads, heads. That's 1 outcome. Okay. Now, you know you're not always going to get heads when you flip 3 coins, so there's other outcomes that are possible. I'm going to start to list them out. You might want to pause the video right here and see if you can identify what are all of the other outcomes when you flip 3 coins, and then see if we match. And I'm going to start talking through how to do it, but you pause it, see if you can figure them out. So here's how I try to think about this in sort of an organized way. I kind of focus on 1 coin at a time. So I know I could get heads, 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 but that 3rd coin could have landed up as a tails. So there's a second option, heads, heads, tails. Now I'm going to think about the 2nd coin flip. Well, that 2nd coin flip could have been a tails. So I could get heads, tails, and then heads on the 3rd. I could get heads, tails, and then tails on the 3rd. So now I've got that 2nd coin flip set as a tails. What if I change the 1st coin flip? Okay, well, the 1st coin flip, what if it was a tails? Well, I could go tails, heads, heads. I could go tails, heads, tails. And now I could also do tails, heads. Yep, already did that one. Got to erase. We could do tails, tails, and heads. Go back to my pen here. And then we could do tails, tails, tails. Okay, in the end, we should have 8 total outcomes. And if you see me struggling to think about all these and you're thinking, well, I'm kind of struggling too, well, there's an easier way to do this. I'm going to show you here in a second. But we do have the sample space. So this listing here, that's the sample space, done. To turn this into a probability model, all I'm going to do is this. I'm going to say, here's all my outcomes. And I'm just going to list the probabilities of each of those outcomes next to it. So because these are fair coins, if there's 8 total outcomes, the probability for each one of these is going to be 1/8. So as I'm just simply writing the probability next to each of these, I'm creating a probability model. And you'll notice if you actually total all of these up, if you add 1/8, 1/8, 1/8 8 times, well, you get a grand total of 1. The probability of everything in your sample space has to total up to 1. So there's a probability model. Now the third question says, if we talk about event A, meaning you get at least one tail, we want to find what is the probability of A. All right, here's one way to do this. One way to do this is go through and just look at all your different outcomes and say where are the outcomes that have at least one tail. So all I got to do is if I see a T anywhere, I'm counting that. So here's one that has at least one tail. That has at least one tail. So does this. So does this. So does this. So does this one. And that one's got at least one tail. So I could look at all these outcomes and say, wow, there's all those outcomes that have at least one tail. That's 7 out of the 8 outcomes. And really what I'm doing is I'm adding 1/8 plus 1/8 plus 1/8. And I'm doing that 7 times to get my 7/8 answer. Now, if you want to use the complement idea, here's a different way to do it. A different way to do it is say the probability that I'm after, getting at least one tail, could be found by doing 1 minus the probability of everything except what you're looking for. Well, if I'm looking for at least one tail, a complement would be anything that does not have one tail. So that would be this. This would be a complement right there. So I could come up with the answer by doing this. 1 minus the probability I don't see any tails at all. 1 minus 1/8, 7/8. Again, I get the same answer, but you're going to notice with probability, sometimes it's easier to find the probability in one way or another. Sometimes it's easier to find the probability of what you're not looking for and then subtract it from 1. All right, let's go back. Let's finish up one final example here. Now, I did promise you I was going to show you an easier way to figure out why were there 8 different outcomes, and a tree diagram is really helpful sometimes. So in a tree diagram, you kind of break it down one step at a time, and you think, okay, I'm going to toss the first time I toss the coin, I could get a heads or a tails. I know those are the only 2 things that can happen. And you kind of branch off from there and say, okay, well, what happens on the second toss? Well, if I get a heads on the first coin, the second coin could be a heads or it could be a tail. And then whichever one of those I get, the third coin could be a heads or a tail. Doing this for each option allows you in the end to kind of identify what each of those possible outcomes are. So you can do that just by following the arrows. Heads first, heads second, heads third. There's HHH. I could go heads first, tails second, heads third time, and that'd give me heads, tails, heads. So I can do that. If you're having a hard time identifying all the outcomes, sometimes a tree diagram is really helpful. So here's our final example. We're going to take a look at a probability model for what happens when people take the AP exam. And these are this is the probability distribution of all the scores on the 2019 AP Stats exam. And you guys know, on an exam, any AP exam, you can get the best score you can get is a 5, the lowest score you can get is a 1, you can get a 5, 4, 3, 2, or 1. These are the proportions of people that got each of those scores. So what we're going to try and do with this is we're going to first try and identify, is this really a legitimate probability model? Does this actually work? Does it fit kind of the rules to it? Then we're going to try and find what's the probability that a randomly chosen student gets a 3 or better, which is your goal on Thursday, May 13th. You get a 3, 4, or 5, you're getting college credit at just about any university or college in the country. And then the final thing we're going to try and answer is, what would be the probability that some randomly chosen student did not get a score of 1? If we want to think about, I want to avoid a 1 at all costs, what's the probability you don't get a 1? So let's look back over here. We'll go back to the Jamboard here, and we will answer these questions. All right, question number 1, explain whether this is a legitimate probability model. Well, I got to identify a few things. First off, does it have every outcome in it? And it has 5s, 4s, 3s, 2s, and 1s. And that is the only thing you can possibly get on an AP exam. There is no score of a 6, you can't get a 3.7, you can't get a 0. So it does have all the outcomes. So I'm going to identify that. It has all outcomes. The other thing I want to identify is, well, let's look at those individual probabilities. They better make sense as probabilities. And to make sense, they have to be somewhere in between 0 and 1. And I don't see any negatives, and I don't see anything bigger than 1. So this is good. All probabilities are between 0 to 1. The other thing that has to make sense is we have to check this. Do all probabilities add to 1? So I'm going to come over to the calculator, and we're just going to check this and see. I'm going to have to move that out of the way. So we're just going to add these up. So 0.147, 14.7% of people got a 5. I'm going to add that to 0.184. I'm going to add that to 0.266. Almost 27% of people got a 3. A score of a 2 was 0.193. And a score of a 1 was 0.21. Now, it's better add up to 1. If it doesn't add up to 1, there's some missing probability or some extra probability. All right, we added up. We total 1. That looks good. So all of these things are checked off. We do have a legitimate probability model. Yes, we do. Okay, question number 2 says find the probability that a randomly chosen student scored a 3 or better. Okay, a 3 or better would indicate this. A 3 or better would mean you got a 5, you got a 4, or you got a 3. So we're looking for a 3 or better. So one way to calculate this, I'm going to indicate this way, a probability of 3 or above, 3 or better. We could calculate that by saying that's the probability of getting a 5 plus the probability of a 4 plus the probability of a 3. So those are all my scores, 3 or higher. And I can add those together, 0.147 plus 0.184 plus 0.266, and we can get that answer. So I'm going to go back to the calculator, 0.147 plus 0.184 plus 0.266. And a 3 or better is what gets you college credit, and the answer to that is 0.597. Now, if you're looking at that and thinking, oh, that's only about 60% of people score a 3 or better. Well, that's true. That's what happens nationwide. You should be glad to know that at Centennial that we have about 90% of our students score 3 or better every year. So we do much better than the nationwide average on this test. Okay, final question, number 3. Find the probability a randomly chosen student did not get a 1. So notice it's a not problem. So the probability somebody did not get a 1. Well, one way to do this, the probability that you did not get a 1, which I'm going to symbolize this way, that's 1 complement. Remember, 1 complement means anything except for 1. Well, not a 1 means you either got a 5, you got a 4, you got a 3, you got a 2. Here's everything that's not a 1. So I could solve this problem the same way that we did number 2 over here. I could add up the probability of a 5 plus the probability of a 4 plus the probability of a 3, and now also add in the probability of a 2. And I'd get my correct answer. But I want you to recognize that I could also do this. The probability, I'm going to use the complement rule. The probability that you get anything other than a 1 is also found by doing the probability of 1, the overall total probability of 1, take away the probability that you got a 1 on the test. So I can do 1 minus 0.210. I'm going to say, let's focus just on those people that got a 1, and let's say what's everything else. And if we subtract that, we're going to get 0.79. Okay? So there's a 0.79 probability that people do not get a 1. A randomly chosen student does not get a 1 on that test. All right, so let's wrap this up here a little bit. We actually used a few different rules of probability in this video. We talked about how any probability has to be a number between 0 and 1. Can't have negatives, can't have above ones. We talked about how if we add up all of the outcomes, we better get a total of 1. We just checked that on the AP exam scores problem. We talked with the dice about how if all your outcomes are equally likely, then you can find the probability of a certain outcome just by counting how many outcomes match whatever event I'm looking for, dividing by the total number. And we use this complement rule a few times. The probability an event does not occur, you can just use 1 minus the probability that that event does occur. So what's the probability I don't get a 1 on the test? Well, we just do 1, take away the probability that you do get the 1 score on the test. And then final thing, if two events have no outcomes in common, then we can find the probability that one or the other occurs just by adding those two probabilities together. This is like what we did when we said, what's the probability that you get a 3 or higher? Well, that meant you got a 3 or a 4 or a 5. You can't score a 3 and a 4 on the test. So we just added each of those outcomes together. And we're going to talk a lot more about what mutually exclusive or disjoint events are in the next video. But two events are mutually exclusive. If they exclude each other, they cannot happen at the same time. And so, for example, getting a 3 and getting a 4 on the AP exam are mutually exclusive. You cannot get both when you take that test. You get one or you get the other. Okay. All right, that's kind of wrapping up the first video of this section 5.2. Good luck. Try the problems and the homework dealing with this. And you can always watch those Simple Learning Pro videos also to help you reinforce these ideas.